Good afternoon, everybody. It is Friday, September 15th, 2023. It is the sixth and last lecture of my mini course of nonlinear contraction theory. Well, it's on contraction theory. All right, so I have here for you the outline, which I wish to quickly review. So we reviewed the history. We did the basic definition on a vector space. I hinted at the fact that there's a lot more linear algebra in chapter 2, which is useful, that I did not cover. We looked at the first batch of example systems, including various types of gradients, including proximal gradients, which is a generalization of projected gradient. We did some neural networks, Luret forms. Then we took a break from the example, went back to the theory, and did equilibria, Lyapunov functions, the Euler discretization theorem, the incremental ISS, the contractivity, the interconnection theorem. And then we did some kind of fun examples. We did the gradient dynamics or the pseudo gradient dynamics in games. And then we did this equilibrium tracking problem, which is essentially, you can think of it as yet another fundamental property of contracting systems, which are time-varying, and the application of that to feedback optimization. I want to go back to that because there's one thing we didn't cover. And so most of the topics, I may likely skip the machine learning application example here. I'm happy to talk about it if anybody is interested offline. Here, this topic, I may skip it. Before I let you go, I would like to, before the end of the mini course, I would like to spend a little bit of time discussing some generalizations, because as I have mentioned to you, as much as I love contraction theory on a vector space with respect to a norm, there are cases where that's not the right tool and you need to use something generalized. We've already encountered one such example. We encountered the problem in which you were not contracting on the full space when the constraints were redundant in the primal dual gradient flow, because that dynamical system lives on a subspace, and you need to define a proper norm for that subspace, not a norm on the full space. Because in fact, what is true for that system is that if you start on a subspace or if you start on another subspace, both of those are forward invariant. So then you cannot hope to be globally contracting, because if you live in a subspace, you're not going to jump from one to the other. There will be one fixed point here and one fixed point there, and whatever you start, it determines your final condition. So I'm going to review that just a tiny bit, and other extensions. Sometimes you're only locally contracting. Sometimes the contraction rate C is equal to 0. So that we need to work on. And also, there is a lot of work out there on contractivity with respect to geodesic distances on Riemannian manifolds. And I would like you to have an idea of what that means, even though I'm going to show you a couple of examples. All right, okay, perfect. So that's the work plan. I have got a lot of ground to cover. So let us, as usual, let me just quickly show you what is happening here. Let me quickly show you one. Okay, the links are not working. Why are they not working? Okay, let's try it like this. Maybe because it didn't find. Okay, so this was the end of last hour, at which point in time I show to you the gradient controller. This controller has many properties. For example, as you observe this gradient flow here, it appears as though you need the knowledge of the disturbance W in order to implement it. And instead, it is a small exercise. In fact, it is an immediate observation that this signal here is equal to y of t, the output of the plant. And you can just measure the output of the plant and implement the gradient controller without measuring the disturbance. Just a little observation. The other thing I wish to say is related to the proximal gradient that we talked about yesterday and before class. Imagine that, sorry, this slide is a bit crowded. I wish to minimize the same cost function as before. So I have an energy function, u comma w, and I want to minimize it with respect to u. So I do the gradient. However, you must take a value in a compact set script u, right? I have a constraint. So your control signals satisfy some type of bounds. So I am going to define the orthogonal projection onto the space of control of signals. And you now can you can verify, as I was hinting at, that the optimal solution to this constrained convex optimization problem is a point of the form u star equal to the projection onto u of u minus gamma gradient with respect to u of the energy. I will leave this as an exercise for you to think about what is the first order equilibrium condition for a strongly convex function constrained to live in a compact set. The global point is either in the interior or on the boundary. If it's in the interior, checking this equation is trivial, as we were saying. And if it's on the boundary, you need to think about orthogonality. What does orthogonality mean? And you get this equation here. And so then, if that's the fixed point, then it is natural to define the projected gradient according to simply u dot equal to minus u plus p of u minus gamma, blah, blah, blah. All right. And as you remember, in a couple of lectures back, I mentioned to you that if the function e, in this particular case, e, is strongly convex with respect to u, then not only the gradient of e, but also the projected gradient of e onto the set u is again a strongly contracting dynamics. So this is still working with different contraction rate and Lipschitz constants, but these are quantities that you can compute. You need to chase through the definitions and compute the right quantities. So this works again, and therefore you're going to achieve equilibrium tracking with a constant factor L over C squared times, of course, the speed at which the parameters are changing, which is, as we knew, the driving force. Okay, so this completes my discussion of the gradient controller. And I will skip the machine learning example that I have in here. I have just added it to the slides. So if you download the slides, you will be able to read it. And I think I actually have various YouTube talks on this already. I'm only maybe going to make a quick point, which is like this. If you look at the recurrent neural network model in the firing rate version, where the nonlinearity is applied outside and the linear map A is applied inside the parentheses, then that is called a recurrent neural network. Recurrent neural network. If you look at the fixed point problem that it defines, so once again, this is the recurrent neural network. I set x dot to 0. That is the fixed point problem, which looks very similar to what we just said about the projected or the proximal operator. So that's a fixed point, and people call this an implicit neural network because, of course, the solution x given a stimulus u and a bias b, the solution x is implicitly defined, right? Is x equal to phi of a of x? It's implicitly defined. And in machine learning, people are interested in saying, I would like to use this architecture. You give me a stimulus u, and I want to compute a solution. I want to compute u as my output of my machine learning model. And immediately contractivity comes into play, because if this is the model that you wish to use, and if you wish to have a model that has a unique, robust solution that you can easily compute, well, then I would argue you want to make sure that your implicit model is contracting in some sense so that it's well behaved. Finally, if you compute the Euler discretization of the recurrent neural network, you obtain, okay, this last equation here at the bottom. This last equation happens to be both the Euler discretization of the first recurrent neural network there, but also, if you go study fixed point theory, this is called the Krasnozelski-Mann iteration for the fixed point at point 2 here. Okay, so in a different discipline, people would never talk about the ODE, just take the fixed point problem and define a certain iteration. It's called the Krasnostedt-Schiemann, and that would be it. Okay, so now, what do you know from everything that we have said so far? Allow me this opportunity to maybe do some redundancy so that we all remember. What we have seen is that if the matrix A satisfies my contractivity or log norm condition with respect to the infinity norm, less than 1, there is a 1 because, you know, there is the minus identity matrix there, right? So select a synaptic matrix satisfying this property, this graph theoretic property that each neuron has incoming synapses with limited weight. Then, what do you know about these 1, 2, and 3 equations? What do you know about equation 1? Well, you know about equation 1 that the recurrent neural network is strongly infinitesimally contracting with the given rate with respect to the infinity norm. What do you know about the second part there, right? The second, you know that the implicit neural network is well posed. For every stimulus U, there exists a unique response Y. And what do you know about the Euler discretization? Well, that's the Euler discretization theorem we talked about yesterday. And the Euler discretization as a finite map, not in continuous time, is discrete time contracting. And as I have mentioned to you, I have an upper bound on the contraction factor for the discretization. It is not the optimal choice because it's only an upper bound, but I can certainly optimize that. And so there is a particular contraction factor that you achieve at a very particular step size. And these formulas, I'm just going to say this, these formulas for the optimal contraction factor and the optimal step size are different from the one you saw yesterday, because yesterday I showed you the formula for the optimal step size for a generic arbitrary norm. Knowing that this was the infinity norm, you can select a better step size. Another aspect of the theory that I have not had the chance to cover, but that I would like to cover right now for you is the following. It turns out, of course, that if you think about all of the bounds that I've obtained, you can also obtain an input to state Lipschitz constant. So from the stimulus U to the state, to the, let's call it to the output of the machine learning model X, what is that Lipschitz constant? And you can write a formula for it. Which, look at this, it kind of looks like the formula that I started this morning when I was talking about marker chain. There is some kind of a induced gain at the numerator and 1 minus the contraction factor at the denominator. All right, so these are useful quantities when you have to use this model for a machine learning application, where you typically need to evaluate a model repeatedly, perform partial derivatives, and so on and so forth, for back propagation and so forth. All right. Finally, after this lengthy introduction, I have now essentially finished what I wanted to say about contraction theory on vector spaces, the standard clean theory. Let me now show to you these extensions. My plan would be to do relatively quickly semicontractivity, local contractivity, and the Riemannian manifold in the first hour, and then I will spend more time to tell you about the weak contractivity case, also referred to as non-expansive case, when the contraction rate vanishes and you have the one-sided Lipschitz constant being equal to or less than equal than 0. And it's tantamount to a LaSalle invariance principle for those of you familiar with Lyapunov theory. All right, so what happens in power grids, flocking problems, and traffic models is that you have a vector field that has either an invariance or a conservation property. I'm going to write generalized versions of this property. What might invariance mean? It means that if you translate the state in an appropriate direction xi by any amount alpha, the vector field does not change. So if you're moving at a certain speed, so if you're performing in a certain way and you now translate me, I continue to move in the same direction. So that's an invariance property. Alternatively, believe me when I say this is equivalent to the generalized version of a conservation property. Well, let's do this little calculation together. Imagine that the total amount of mass in a certain system is conserved. What does that mean? That means that at node 1 plus node 2 plus at node n, my quantity is conserved. So notice that the sum of the entries of X, it's just the vector of ones, 1n, transpose multiplied into X. So now imagine that I claim that this quantity is equal to a quantity, I don't know, let's call it capital C, and it is time independent. Allow me now to differentiate this equation with respect to time. What do I obtain if I differentiate the left and the right-hand side? Well, it certainly is true that the derivative of a constant is 0, last I checked. And on the right-hand side, 1n does not change. And then I obtain, well, imagine that I have that x dot obeys an ODE like that. Then wouldn't it be true that 1 transpose n times f of x has to be 0 if my system preserves the quantity, right? So if I have maybe a continuum approximation of traffic, the quantity of commodity that is moving on the network is preserved. So the vector field 1n transpose f is equal to 0 everywhere. Here, as I said, at the bottom here, I can relax that and make it even a little bit more general. And I can look at the case where eta transpose f is just a constant. Maybe, why is that interesting? Because maybe your quantity is not constant. Maybe there is an input u, which constantly throws additional commodity into the network, in which case maybe you have 1n transpose u, and provided 1n transpose u is constant, then we can still handle that problem, right? Okay, when you look at these two formulas, these are integral formulas. There are no derivatives. And in fact, I could do the whole theory just with those formula without assuming that f is differentiable. That can be done. However, because it's simpler, allow me to now differentiate f and compute the Jacobian. It is a tiny exercise which you can do in the comfort of your homes to check that if you differentiate with respect to x, the first and the second equation, you obtain these other two equations here. Oops. This equation and that equation, right? So it's because you take the Jacobian with respect to x, that's what you get. So because if you move in the direction xi and f does not change, that means that df into xi is 0. What name would you give to these two equations here? These are directional derivatives, yes. Let me give you a hint. I know it's hard to guess what I'm thinking. df, the Jacobian, is a matrix. And I have a matrix times a vector is equal to 0. What does that mean for the vector xi? Xi is an eigenvector corresponding to the eigenvalue 0. So this equation is an eigenvector eigenvalue equation for the Jacobian of f for everywhere in space, for all x. These two properties hold. So what have we understood? Very simply, that the Jacobian has an eigenvalue equal to 0, whether you have a translation invariance or a conservation property. An eigenvalue is equal to 0 everywhere in space, and in fact, even more so with respect to an eigenvector, a right or a left eigenvector, which are constant. That's an even extra additional property, right? Do you have any hope to prove that your matrix is Hurwitz or your one-sided Lipschitz constant is negative if an eigenvalue is equal to 0? Well, of course, the answer to that is no. There is no hope to prove global contractivity because you are invariant or because you have a conserved quantity. If the quantity is conserved, you can have a system at different level of conserved quantity. For example, you may have a box with chemical with a certain amount of chemicals, it goes to an equilibrium. If you throw more chemicals inside, it goes to a different equilibrium. You're living with a different amount of chemical concentration. So because there are no nuclear reaction in your chemical plant, right? Something is conserved, right? All right, perfect. So this is telling you that you have this, it's actually the same problem as in the primal dual constraint optimization problem we discussed, where the Lagrange multipliers live in a subspace anytime the constraints are redundant. Okay, so a canonical example of this is, let me do this quickly because I do not want to talk about consensus algorithms for too long, but we're all familiar with that, with this literature. If you have something called the continuous time Laplacian flow defined over a graph, suppose under some graph theoretical connectivity condition on the graphs that the kernel of the Laplacian matrix is a subspace and it's generated by the vector 1n, then you can take the state of the system, compute the average, which is a projection along the kernel, and the perpendicular component of the state. You can take your state and say, this is the average and this is the perpendicular. Right. And this is a picture of the kernel of the operator L, which will be the kernel of a seminorm that I will define in a second. And this is the space perpendicular to it. All right. Perfect. So it turns out that because of the properties of the Laplacian, in particular, I did not assume symmetry. So what the property in this case is L1n is equal to 0n. That's the standard property. And so if you remember from the previous slide, I'm multiplying on the right. So this is the translation invariance. So if you sum a alpha times 1n to the state of the Laplacian system, the solutions are just translated by the same amount. So it's an invariance property, right? And so it turns out that, look, I did a little calculation. It seems to me that you can write an ODE for the perpendicular dynamics and an ODE for the average dynamics. One is along the kernel, the other one is perpendicular. And it seems to me that the average value does not, so this is a system in chain form. So the perpendicular dynamics affects the horizontal dynamics, the average dynamics, but not the converse, right? So the perpendicular dynamics is well defined, independent of the average of the state X. All right. So here's a slide where I show you 3 examples. So this is the Laplacian flow that we just saw, and it has this translation invariance. The second example is a coupled oscillator. It's called the Kuramoto model or the Kuramoto-Sakaguchi model. I could give you a mini course just on that, and I don't have that much time, but let's put it this way. The state at each node is an angle, and so the state of the system is n copies of the torus, and the differential equation describing the evolution of the system is a combination of trigonometric operators, trigonometric functions applied to angular differences. And so inside that emphasis there, you see B transpose theta. B transpose is an oriented incidence matrix, and when you write B transpose and you apply it to state vectors, you get entities of the form theta I minus theta j minus theta k, and so on and so forth. So only angular differences appear in there. And it turns out that the Kuramoto model, when you add a shift to it, this phi is non-zero. It's a more generalized model. It's called the Kuramoto-Sakaguchi model. But even after you have generalized it, it turns out that if you take all of the angles of the model and you add a constant rotation to all of them, call it alpha, then theta plus alpha identity, it's the equivalent of a translation invariance for the Kuramoto model. And finally, the last example, I have been claiming to you that you can just shift when the constraints in the primal dual problem are redundant, I can just shift, you live in a certain subspace, you have this translation invariance. And this is the precise expression for what that translation invariance is, right? So you can translate lambda by any amount alpha along the vector v, and v has to live in the kernel of A transpose. You can just check. That's very simple. All right. So this is the translation invariance, which in differential geometry is referred to as a symmetry. And it turns out that in all cases, you think you are in a large space. It could be Rn, it could be an n-dimensional torus, it could be Rn plus m, n being the primal, m being the dual. But because of this invariance, really, you can think that your system is actually evolving in smaller spaces. This perpendicular space that I just showed you, for what does the perpendicular dynamics do in the consensus problem, perpendicular to the vector of of ones. So here in differential geometry, these perpendicular spaces, when you remove the translation invariance, are called quotient spaces or reduced spaces, and people write this little formula where say it's really Rn, but then I remove this invariance, and it turns out that if there are k redundant constraints, then you remove Rk. And here, even though we would be working with angles, so really I am on the torus, which is not a vector space, but as you do this reduction, it's really tantamount for everything that follows. You can just think of that as Rn over R. If you want to think that the angles, instead of living in a circle, are just arbitrary real numbers and everything is periodic, that's perfectly fine. And so there are two theorems here that I want to tell you before I move on. The first theorem is that, okay, as I had mentioned, and this is differential geometry essentially, that whenever you have this invariance, the perpendicular dynamics is always well-defined and independent of the dynamics, which will be horizontal, which is along the translation. Because you get this system in cascade form. I said chain a few minutes ago. I meant to say cascade. So the perpendicular dynamics is invariant, and the solution of that affects the other variables. And so it's important, we can just focus on the perpendicular, also called reduced dynamics. And now the question is, okay, Francesco, after you have done this reduction and you're looking at the perpendicular dynamics, why are you talking to us about this perpendicular dynamics? Because that's what I am going to hope to prove is contracting, right? You cannot have, it is impossible to have, because of the invariance, strong contractivity on the full space, but you can certainly ask for contractivity on the reduced space. So now we are going to see what does it mean to satisfy contractivity properties on the reduced space. However, when you move to the reduced space, you need to take your dynamics, which maybe is expressed by a simple operation, and you need to start to perform various operations on it so that you properly define the dynamics on the reduced space. In this particular case of the Laplacian flow, it was very easy to pre-multiply L by pi n. It's not a big deal. But in other cases, it can be complicated to write down explicitly an expression for the dynamics on the reduced space. You don't want to do that because the original data of the problem, when people tell you this is the vector field, they give it to you on the full space. And you don't want to have to do a lot of manipulation. Then you write the condition for contractivity on the manipulated quantities, and then you need to go back. In other words, you want to express the contractivity conditions back as a function of the original data. So it's just a lot of, for example, even a Markov chain lives in a reduced space, but people always express the ergodicity property of the Markov chains as a function of the original matrix that is given to you, not as a function of some derived quantity later on. Then you lose the intuition and what is the condition there, right? So the point is that you wish to design a theory that allows you to manipulate things on the full space and prove contractivity only on the subspace where you live. And so this theory is a theory of seminorms. So a seminorm is a norm. No, a seminorm is almost a norm. Is a function that satisfies homogeneity and subadditivity, the triangle inequality, but it does not satisfy positive definiteness, which is the property of a norm. Positive definite means that x is equal to 0 if and only if x is the vector of zeros. So this is not true anymore. Here, every point on the kernel space, all of them are going to give you 0 when you apply the seminorm to them. Does that make sense? All right. So there is a bunch of results which I have no desire right now to impose on you. It's a little long story, but the point is this, that the key ideas are that you now have a new norm, it's well, the equivalent of a norm, and you want to repeat the whole theory that we've done so far. So what would be that theory? Well, you want to define something called the matrix seminorm. You want to define something called the matrix log seminorm. So now you have your log norm, or the equivalent of, and you want to talk about the vector field F on the full space, satisfying the supremum of the log norm of the Jacobian is less than equal than minus C. But I said something wrong on purpose. The supremum of the log semi-norm of the Jacobian is less than 0, right? So here I am using this weird triple bar instead of double bar to denote a semi-norm. And so here at the bottom, the contractivity condition, or I should say better, the semi-contractivity condition uses the log semi-norm. It's the same theory, but you know, you gotta work with the flow. And then, but the good news at the end of the day is very, very simple, very, very intuitive. And this is the good news that I would like to just share with you here. If I am able to. I am unable to move the good news is that if you do the right definition and you do the right theory and your vector field has this invariance property, well then proving that the vector field on the full space is infinitesimally semicontracting, which is to say the supremum of the semi-log norm of the Jacobian is less than or equal than C, it's exactly the same as proving that its reduced dynamics on the correct perpendicular space is strongly contracting. Which is what you wanted to prove essentially. So you can work with the original data, the original vector field F, and just do all of the calculations with F, and it will imply contractivity on the subspace. Does that make sense? Which is what we did. Which is what we did in the primal dual case, because we did the calculations for the LMI using that pi projection in the middle of the P matrix. So that P matrix was not positive definite, it was positive semi-definite. Therefore, that was a semi-norm. So why don't I do things more slowly, which is what exactly this slide is doing. So in other words, a very natural way of defining a semi-norm is to consider a positive semi-definite matrix P, not positive definite. And the matrix P would have a kernel, and then you define the semi-norm as X transpose PX. Also, a very natural semi-definite matrix is precisely this orthogonal projection onto one end perpendicular. It's called the centering matrix in statistics. It's an orthogonal projection onto the subspace perpendicular to the space one end. It's a canonical one. There is even a beautiful little expression in coordinates without having to do matrix manipulations. Again, it's an orthogonal projection, so the eigenvalues are zeros and ones. Of course, it's positive semi-definite, right? And then what we did the other day with the redundant constraints in the primal dual problem was to essentially to say that we looked for a negative L, right? And we showed that the semi-contractivity LMI was satisfied by the primal dual matrix. And that's exactly calculating the 2 log semi-norm of the matrix. That's what I did the other day. So this is the theory that better explains why can I handle redundant constraints in the same. I'm going to skip the Laplacian flow. Or maybe let me just do it. It's super quick. The Laplacian matrix is lower bounded by its smallest non-zero eigenvalue times the projection onto one end perpendicular. So you just think about the geometry and the property of the graph, and that's what you get. On top of that, Laplacian matrix commutes. This is the symmetric case. Commutes with a projection pi n, which means that you can take the first equation, and because of the second equation, you can rewrite it like that, because when you anyway, and this is exactly the contractivity, semi-contractivity LMI, which tells you that the log semi-norm of minus the Laplacian matrix with respect to the 2 comma pi n. So here I'm using as seminorm pi n is equal to minus lambda 2, the algebraic connectivity of the graph. And so this is the one-sided Lipschitz constant of the Laplacian flow. Does this make sense? This is a linear flow. This is overkill. This could potentially be understood to be overkill for just a linear dynamical system. But this has the advantage that it works for a nonlinear case. And so here's the nonlinear case, which is of great interest because there's been a ton of work on Kuramoto models and others. So here is the dynamics. It's the same ODE that I wrote earlier. Earlier, I wrote it in vector form. This is in components. It's easier to read it in components. It is telling you that at each node, the state variable is an angle. Without the interaction, each angle, each node is just an oscillator. You are rotating at the node natural frequency equal to omega I. Does this make sense? So up until here, it's elementary. At each node, you have an oscillator. It's oscillating. Perfect. The interaction between the nodes is described by a graph. Allow me to select it to be undirected. So the collection of non-negative, of positive weights Aij is symmetric, right? Aij is equal to Aj. So these are the weights on the graph. Each node I may be connected to other nodes J. What does it mean to be connected? It perceives a term, some kind of an interaction strength, right? Which is Aij modulated by a certain angular difference. It's theta I over theta j plus the next. If you want to set this to 0, you get the Kuramoto model. When it's different from 0, it's called the Kuramoto-Sakaguchi. Sometimes people call this the frustration parameter because when the two angles are equal, without the frustration parameter, the interaction is 0. With the frustration parameter, even when you are right on top of each other, you're being pushed away. There's a kind of like, if you're forced to be on top of each other, you perceive this. It doesn't matter. Okay, so now this is a system that is hard to analyze with linear tools. However, we can analyze it with nonlinear tools and with exactly the same tools. It works like this. So I can take the nonlinearity there, right? And I can rewrite it as the algebraic sum of two terms, cosine phi, which multiplies this term, and sine phi, which multiplies the second term. And I am going to just call them names because I like to call my things in intuitive names. I will call this the odd vector field, and I will call that the even vector field. Right now, you don't know why I'm calling them odd. I'm just using this name. Well, that's because if you multiply theta by -1, this is an odd function of theta. And if you multiply theta by -1, it doesn't change. So it's an even function of theta. Sorry, for a second I thought that I had a smarter reason to use that name. Now I realized what it was. All right, fine. So now the two, why did I decompose it into these two terms? So if you have an odd function and you calculate an odd vector field and you calculate the Jacobian, in this case, it's going to be symmetric. And if you have an even function, an even vector, yes, exactly. It is going to be skew. So the point is that now we don't have the time nor the interest, I think, to go through and calculate everything. The point is that these two odd and even vector fields have Jacobian with special structure. And then I need to just simply compute, well, I need to compute their logarithmic seminorm. And I will still use the same one that I used for the Laplacian flow, so that pi n seminorm. I'll use the same pi n. And now, for example, let me do only one of them for you. So for the odd piece, right, the one up, you can see that they're both on the slide. It turns out that, well, actually, when the frustration is 0, the cosine of phi is 1, and the sine is 0. So in some cases, when I remove the phi parameter, I don't even have the second term, I just have this. And it is well known that the Jacobian of this term looks like a Laplacian matrix. It's a Laplacian matrix with coefficients that are state dependent. So here, this is equal. I use the symbol L to denote the Jacobian of that. It's equal to minus the Jacobian of that. And so, but then this is just equal to lambda 2, like in the linear case. Does that make sense? It's really the same calculation. It's just that the Laplacian is function of theta, and I get a lambda 2, which is a function of theta. In fact, more precisely, this is lambda 2 of the original unweighted graph, sorry, undirected graph without the angles, but then it happens to multiply a function of a function of theta. Does that make sense? So without too much effort, you can reapply the same theory from before and show that your system is strongly semi-contracting. Strongly semi-contracting. Now, there is something that I haven't said so far. And by the way, to make this equality come true here, you're using the fact that the Jacobian of the matrix looks like minus the Laplacian, so and the Laplacian satisfies certain equality with the oriented incidence matrix and so forth. Now, but there is something that does happen, and it is critical. So when you compute this Jacobian, you do get a matrix that looks like a Laplacian, but you need that cosines of angular differences are positive. Otherwise, you have a graph with weights on the edges which are negative. And if that's so, then you have a weight, you have, I don't know what to call it, you have a weighted graph with negative weights and positive weights. And then all of a sudden, I cannot, maybe Claudio can, but I cannot guarantee anymore that the smallest eigenvalue is still positive. We can talk about it later, Claudio. So I am going to say that whenever all of the cosines of all of the pairwise angular differences are positive, then the weights on the graph are in fact positive, and my analysis goes through perfectly well. And so I am going to require that if I look along each edge and I look at the maximum pairwise differences, I need to require this maximum pairwise differences to be less than equal than, actually strictly less than pi over 2, so that the cosine is positive, right? The cosine is 1 at 0, and then at pi over 2 is equal to of 0, right? So I want to remain positive. So I need pairwise angular differences to be less than pi over 2. If you go to larger angles, then that's not true anymore. Does that make sense? So here's the picture that I want to show you before we take a break. Maybe. What did we do here? We considered a graph with 13 nodes. And we wanted to plot something. It's very hard to plot in 13 dimensions. So what did we do? We have a 13-dimensional space. We just picked a 2-dimensional plane, like a subspace. I think it was through the origin. Maybe it was an affine subspace. I forget exactly what we did. Just a subspace. And at each point of the subspace, we are going to plot the key quantity that I have been talking about for a while now, mu of the Jacobian of f, which is function of theta, right? And I pick theta in a 2-dimensional, well, theta really lives in the torus to the 13th because there are 13 nodes. But then what I do is I pick theta in a 2-dimensional subspace, okay? Randomly generated, something like that. Does that make sense? What am I plotting? I'm plotting the log norm of the Jacobian. But what log norm? Actually, I'm plotting the 2 log norm and not the 2 log norm. I use the semi-norm, right? Because otherwise it doesn't work. Pi n. And I hope for this to be negative. And then I do a color plot. So the red colors, mu 2 pi n is negative, and the blue color, mu 2 pi n is positive. Does that make sense? So now you can see, you can just see there are regions where my dynamics is contracting. Well, okay, I should say it's semi-contracting, but okay, mod out, remove the symmetry. So don't worry about the rotational symmetry. Your system is contracting in all of these red regions, and it is not contracting, it's expansive in the blue regions. Does that make sense? Very cute, very cute, very cute. So, very cute. So this is not a global contractivity result, right? This is a result that tells you that you have regions we know something about this partition of the space, right? I can talk about that as well. But basically, this motivates the study of problems where you have contractivity in a region, maybe compact, and you would like to know something about the behavior of a contracting system, well, of a system that is contracting only locally. Only locally. And I'll tell you right now already the punchline so that I'm going to run out of time. So I'll tell you the punchline, tell you the conclusion at the end, at the beginning, right? So that even if I run out of time, the conclusion is that in each of these convex regions, you can have at most only one equilibrium, but you could have zero equilibria. It could be that the dynamics enter the region and it doesn't stop and it leaves the region. Or it could be that it enters slowly and then the speed is exponential decay and it stops. And when it stops, that's an equilibrium. And now you have an equilibrium in a convex region where the system is contracting. I can prove that there can be no other equilibria in that region. And the proof is a simple proof, because if you have two equilibria and the segment connecting them is the system is contracting because the set is convex, right? So if you take the segment connecting to equilibria, you write the usual formula. The distance between the two solutions originating the two equilibria should be decreasing. And it's not decreasing because there are two equilibria. So it's a contradiction. So it's not a rocket science theorem. It's pretty obvious. It's the same theorem for the uniqueness of the equilibria in Rn. It's just that here you're applying it locally on a local convex set. Conceivably, you could have a situation where you are contracting on a set that is not convex. And now maybe you have more than one equilibrium because I cannot draw the segment between them. All right. This is the primal dual case, which you have already seen. And I have yeah, why don't I just show you? So this is the picture, right? I have a convex region where right now, let's not worry about the semi-contractivity part, okay? So remove the symmetry, forget about the Kuramoto coupled oscillators. This is just an arbitrary dynamical system in Rn. I select any norm. It doesn't need to be the 2 norm. It certainly does not need to be the 2 comma pi n. And I am just interested in knowing. So I have a region when I am contracting. For example, this region looks like this right here. At where you see the exact white, that's exactly where the log norm of the Jacobian is 0. Inside, it's strictly negative. Outside, is strictly positive. And you would like to talk about the basic property of contractivity that you want to hope for is the existence of an equilibrium and the fact that the trajectories converge to it. So this is the basic thing that you would like to establish to get started, right? So, right, that's right. So here, what did I write here? Forgive me, I want to follow this step by step. Given a norm, consider a set, and imagine that x dot equal f of x satisfies that the log norm of the Jacobian is negative, but not everywhere in a set S. So as I said to you, trajectories slow down and approach each other while they are inside S. Does that mean that they stop? Not necessarily. Okay, so here I have 4 lessons, and then we take a break. 4 lessons to share with you on this problem. And I think this is actually unpublished work, so maybe I will not put this video on the web just yet. The first property is that, remember, I mentioned to you the other day that the one-state ellipse is constant has 2 definitions, the integral and the differential. We even proved it, actually. Well, it turns out that if you're working on a set, and if the set is convex, everything works the same. So the theory that I have presented for you works, even if you're not globally contracting, so long as the set you're working with is convex. If it is not convex, then I am afraid, I am sorry to have to inform you that the 2 definitions are not equal any longer. And the one that you really want to use is not the integral, but it is rather the differential one. So continue to work. You can still say things, but you better talk about the supremum value of the log norm of the Jacobian rather than the pairing. My beloved pairings do not work anymore if the set is not convex. You can take a convex subset of the set, in which case you're fine. Well, okay. Now, then I have a really cool result that I would like to tell you. So intuitively, if you are so lucky that you sample a point, and oh my goodness, how lucky I am, at that point f is 0. Suppose that you're magically gifted and you know how to pick random points and you find it, okay? So then you don't move. If you find a ball around it, ball in the norm, right, with respect to which you are contracting, then you can prove easily that the ball must be contracting because you're inside the region of contractivity. Does that make sense? So if you find an equilibrium, then the next thing you can do, you can actually try to draw as large a ball as you can around the point. Well, here it's not quite centered at the point, right? Like, what am I doing here? This is terrible. Let's move it around. Let's imagine that my purple circle, it's still all inside the red region. The region could even become very thinly red, so very tiny contraction rate on the boundary, but inside, okay? Well, then it is clear that every trajectory originating in that disk will converge exponentially fast to the equilibrium point because you apply the same formulas and, all right, fine. That is if you are so smart, smarter than I am, to be able to just eyeball it and say, the equilibrium is there. But in large dimension on a computer, that's not so easy, huh? So forget that. The other thing is this. Suppose you take a point, now can you see it's x bar? I meant to, this is x with a bar on top of it. You pick a point x bar, and you look at the vector field, and the vector field is not equal to 0. Sorry, you're still moving, like you want to flow away. Then you ask yourself the question, would it be true that I will stop, or will I go outside? Will I leave the red region where my log norm is negative? Okay, then you ask yourself the question and you think about it. Okay, you know what? Allow me to draw center that x bar. I will draw a sphere as large, a ball in the norm. Here I'm using the 2 norm, so I'm doing circles. But I could have drawn a box if it had been the infinity norm, right? Or to draw a circle, draw the unit, a ball as large as you can in the norm that you are given, so long as you remain inside the red region. Does that make sense? So now you can play with f at x bar, and you have a radius, and you have a contractivity rate. When you kind of think about this, you say something should happen here, right? In fact, I don't care about the f, I care about the magnitude of f. If the magnitude of f is relatively small compared with the larger is the radius, the better it is for me, right? And also the larger is the contraction rate. Does that make sense? Well, that's exactly the little theorem. The little theorem tells you that, oh, no. Yeah. Good things happen. Let's decide what the good things are in a second. Good things happen when the speed at x bar, maybe I'll call that the residual speed. You find a point, it doesn't move, is upper bounded by the contraction rate times the radius of the ball that you can fit. If this condition holds, then the good news is that the entire ball that you drew is forward invariant. So that means that every trajectory starting inside this ball cannot leave the ball. And now you have a contracting system with the convex forward invariant set. Therefore, an equilibrium must exist inside the ball. Does that make sense? So this residual being sufficiently small is a sufficient condition for the existence of a fixed point. I still don't know where the fixed point is, but I do know that if I can sample the space and I find a point where I move slowly and I can draw the ball and I'm inside the region and the residual is less than c times r, I know there is an equilibrium point in there. Very nice, very nice. Well, anyway, I've gone past an hour, but the other conditions are cute, but not nothing. I'll stop here for now. Thank you. Good afternoon and welcome back. After the break, this is the last stretch. I would like to maybe simply just review where we are at. So this is the outline. We're looking at generalizations, and we've studied some elements of semicontractivity. We've seen three examples: the Laplacian, the Kuramoto, and the primal duo. That had all the property of being invariant under translations. In the lecture notes on the book, there are systems which have a conserved quantity. For example, in traffic networks and compartmental systems studied in biology, medicine, and other ecology and other problems, you have a conserved commodity in the system. And then there is a theory of semicontractivity that is applicable to that, and it's discussed in the book, but I'm not going to have time to do that. We talked a little bit about local contractivity, and we've seen that if your set where the system is contracting is convex, it may have no equilibrium, or it may have one equilibrium. I did not quite show you an example, but it can certainly happen. Please believe me that even if you're contracting on this region, by the way, remember, the contractivity is a property, if I take the log norm of the Jacobian, has to do with the Jacobian. But if I take a vector field f of x and I sum to it a very large constant drift term, so, you know, like f of x plus a vector v, and v is very, very large, then even if you're slowing down, it will not stop because v will carry you outside, and the log norm of the Jacobian will tell you nothing about v. Or another way to put it, if you do f of x minus f of y, the constant terms are disappearing in the differences, right? So you can enter the region and leave. But, so you have zero equilibrium. But if there is one equilibrium, there can be no more than one. There's one equilibrium only. So the result is that basically a locally contracting systems on a convex set has at most one equilibrium, 0 or 1. So in the Kuramoto model, in that picture that I showed you with the red and the blue, we were able to characterize the regions, and we are able to say in each one of those little regions, there's either 0 equilibria or 1 equilibria. And then we count the regions, and that's an upper bound on the number of equilibria, which is a notable thing because in general, it is quite difficult to count the number of equilibria in a Kuramoto model. Oh, yeah. If there is an equilibrium in a contracting region, it's implicit in something that I said. If the equilibrium is inside, draw the largest ball containing the set, and that's a forward attractive set and a forward invariant set, and the point is. All right, so there are two other generalizations that I want to briefly discuss in the remaining time. One is weak contractivity, which other people call non-expansiveness, and maybe I should switch language because I kind of like that too. And then I want to talk a little bit about the Riemannian case. So here are 4 pictures of systems that are weakly contracting. You cannot see them, so sorry about that. Let me make this big. The first one on the left is a solution like this. This is a weakly contracting system. All solutions go to infinity. So it's not contracting. So it could be that solutions go to infinity. Or it could be that solutions oscillate. This is x1 dot equal to x2, x2 dot equal to minus x1, or another way to put it is x1 double dot is equal to minus x1. It's the harmonic oscillator. The matrix associated to this is 0, 1, minus 1, 0. And the mu2 of that matrix is equal to 0. Because that matrix has, it's actually skew. And if you just write A plus A transpose, you get 0. So this is a dynamical system that is weakly contracting. It does not contract with respect, but it also does not expand with respect to the two norm. And it just happens to be, in this case, the case that you have periodic, you see this, right? These are curves, so you keep oscillating, of course, right? The distance between trajectory does not increase. The distance between trajectory does not increase. But does not decrease either, and you do not converge. It does have an equilibrium, so that can happen. Whereas in this case, there was no equilibrium. By the way, suppose I give you either a trajectory that goes to infinity, or I give you an equilibrium. What do you know about all of the other trajectories? I mean, we know that the Lipschitz constant of the vector field is less than equal than 0. Now it means that the time derivative of x of t minus y of t must be less than equal than minus c x of t minus y of t. Huh, but c is 0. So I did not write the right formula. Sorry about that. That's what I'm supposed to write. So the distance between trajectory may not increase. So if you pick any other trajectory here at the same time at which that particle is going to infinity, I would like to tell you that the distance between these two trajectories cannot increase. So if one trajectory goes to infinity, well then, it better be true that the other goes to infinity as well, because the trajectory that's going to infinity is carrying with it every other particle. They're all going to infinity. There's no way around. And if this trajectory is a fixed point, well, then you are not going to infinity no matter where you start, because you are moving inside the ball centered at the fixed point with the radius given by the initial condition. Draw that ball. It could be a sphere, it could be a cube, it could be a polyhedral set. No matter what the norm is, you are not leaving that ball because your distance, well, the equilibrium is not moving, right? So therefore, okay. So the first theorem about weakly contracting systems is that they satisfy a dichotomy. A dichotomy means either possibility A or possibility B. There are no other possibilities. And the two possibilities that either every trajectory goes to infinity or there exists an equilibrium point. Does that make sense? This is a dichotomy that holds for weakly contracting systems. If you study the Laplacian invariance principle, it does not tell you this because the Laplacian invariance principle is for different purposes. And it is related to the fixed point theory, right? The fixed point theory here would tell you on the left, no fixed point. On the right, there is a fixed point. All right. Now, when I said the dichotomy is there exists at least one equilibrium point, I did not want to say, I don't want you to understand that it's unique. That's not true. Here's another case. This dynamics here is x dot equal to minus Lx, where L is a Laplacian matrix. A Laplacian matrix has the property that it is Metzler. All of the off-diagonal entries are positive of 0. And it satisfies this property. The row sums of the Laplacian matrix are 0, right? You remember this, right? These are properties from graph theory. Now, this is an eigenvalue eigenvector equation. So one is an eigenvector, 0 an eigenvalue. But it's Metzler. So as you recall, the infinity log norm of minus the Laplacian. Sorry, I apologize. I made a mistake. Minus L is Metzler. Forgive me. The off-diagonal entries of the Laplacian are negative or 0. Diagonal entries are positive. Minus, when you apply the minus to it, it's the off-diagonal entries become positive. So now, this matrix is Metzler. So this is equal to the max minus L1n overall I. This is the ith entry of that. Row sums you should take the absolute value of the off-diagonal entries, but they're already positive or zero, so you don't do anything. But then this is exactly zero, right? I mean, it's trivia. It's just what I'm trying to say is that if you know these two properties, saying that the infinity log norm of minus the Laplacian is equal to zero is just a transcription. I don't mean to make it more complicated than it is. It's just obvious. It's minus L is Metzler, and L is an eigenvalue in the kernel. Sorry, an eigenvector in the kernel of one, and so it has zero log norm. And what do we see? So the system is non-expansive, right? It's weakly contracting the law with respect to the infinity norm, not the two norm. So here we had the harmonic oscillator. It has one equilibrium, and all trajectories are periodic. Other than that, here we have a few more equilibria. It seems to me that it is an infinite number, right? Because you know there's an infinite number of equilibria, and it just so even happens to be the case that each solution converges to one equilibria, not necessarily, not the same. In fact, not true, right? So this could happen. You could have one equilibria, you could have an infinite number of equilibria, you could have two equilibria for all I know. A theorem you can ask the question, is it true that the set of equilibria is convex? So with respect, if your system is weakly contracting with respect to the two norm, it is true that the set of equilibria is convex. If it's weakly contracting with respect to a generic norm, I believe it's true that equilibria are connected by paths. So equilibria are path connected, but it does not need to be a segment. It can, all right. Right. And here's yet another case of a system which is weakly contracting, and it has a single equilibria and all trajectories converge to it, which is different from the first equilibrium for the first case, right? Because there was no convergence here, an infinite number there, this one, and you have global convergence to it, right? But this is still part of the dichotomy. The dichotomy says that so there are only two possibilities: no equilibrium, every trajectory is unbounded, or if you are bounded, you cannot have you can have periodic evolutions, but there must exist, or you cannot have chaos without any fixed point. There must be a fixed point. There's at least one equilibrium, every trajectory is bounded, and one more property that I have not yet said, and this is, okay, so basically in this area, the name of the game, what is the problem? After you have understood this dichotomy, you say, okay, if everything goes to infinity, okay, not all that interesting, but fine, it goes to infinity. Okay. But if I have an equilibrium, the next question is, when is it true that that equilibrium is globally attractive, right? When is it true that that everything goes there? By the way, every equilibrium is Lyapunov stable, not asymptotically stable, but Lyapunov stable, because you know that if you take any other trajectory, you cannot go away from it. So you remain in a ball around the equilibrium. So you know every equilibrium is stable. The question is, when is it true that an equilibrium that is stable, it's also asymptotically stable, okay? And there is a beautiful little construction by Enrico Lovisari that was published in a paper with Ketan Savala and Giacomo Como. And the proof is very, very cute. And the proof says that if you take this equilibrium and it's locally asymptotically stable, then what happens is that every trajectory in a little neighborhood goes inside. And then even if you are far away, it's like a funnel, because every local trajectory goes inside. The trajectories that are far away have to come in a little bit. And then you repeat this, and a finite number of times, because okay, now that all of the trajectory in the little neighborhood have collapsed, then the ones that were outside have to become closer, and then they collapse. And so basically, this is not quite part of the dichotomy theorem. This is like a second part. But in the case in which you have an equilibrium, then if the equilibrium is locally asymptotically stable, then it turns out that it is unique and it is globally stable. Because now, if the funnel is coming in, you cannot have another equilibrium. That's not possible. Does that make sense? So this is the beginning of a beautiful theory for non-expansive or weakly contracting dynamical system in continuous time. The discrete time case is different. Yeah.
So in this case, the last You have a single point, and this is weakly contracting.
Yeah,
Rather than strongly.
it's weakly contracting, but that point is, I additionally have another bit of information. I know that that point is locally asymptotically stable. So that's what I'm trying to say. Is there is a region? So I know the system is weakly contracting. I know I found an equilibrium, and I know for some reason that it is locally asymptotically stable. Then it is globally asymptotically stable.
So if there's one equilibrium, and it's not locally asymptotically stable, it's just one equilibrium, then it has to be the trajectory is around the number. Any other
If it is well, as we said, every equilibrium has to be stable because of the non-expansiveness property. What's your question? Are the solutions periodic?
Or just the only possible
every trajectory that starts in a ball centered at that equilibrium remains in that ball. And if it ever comes in just a tiny bit, that's it. Now you are in the slightly smaller set, so you cannot diminish that. Your distance can never increase. So it's almost like a little trap. If you come in, now you're in. And then, so yes, if you want to forever, so the distance cannot increase. So then, as you know, it must have a limit, right? As time goes to infinity, the distance between the equilibrium and any trajectory must have, it's a diminishing function or constant, and it is lower bounded because 0 is the lower bound. So it must have a limiting value. So in the end, you approach a ball in the norm. But it doesn't need to be the ball of radius 0. There is also another proof based on a completely different strategy. So imagine that your ball is that your norm is polyhedral. A norm is polyhedral when the unit ball is composed of a polygon. So you're on a polygon, maybe a square, the diamond, or even more general. Okay, and assume that your vector field is analytic. Okay, I don't know if you guys remember, analytic functions are defined to have the property that the function is equal to the Taylor expansion everywhere, right? And analytic functions are constrained in many ways. They have really strong properties. And one of them is called the analytic continuation property. So if the analytic function, is equal to another function on a continuum little domain, then it must be equal everywhere to that particular function. All right, perfect. Polyhedral boundary. I'll just drop it right now. I don't remember all the details of the proof. Because of analytic continuation over any one of the boundary of the polyhedral ball, you can prove that the norm must decrease. Otherwise, a certain quantity goes to infinity, which is not possible. So I'll just like that. So the point is this: if you have a polyhedral norm and you're weakly infinitesimally contracting, and you found an equilibrium, then that equilibrium is actually asymptotically stable, without having to check anything more, just analyticity, non-expansiveness, and polyhedral norm. All right. Okay, fine. Let me just say that in ongoing work, Veronica is writing a paper in which we show bounds that look like this. So what does it mean? If you have an equilibrium that is locally asymptotically stable for your non-expansive system. In fact, let's make it a little bit easier on us. Suppose it is locally exponentially stable, which is actually rather easy to check because you compute the Jacobian, you evaluate it at the equilibrium, and you look at the eigenvalues. If all of the eigenvalues are in the left half plane, as you well know from your even the linear courses, the linearization is exponentially stable at the equilibrium. So now you have a well-behaved equilibrium point, which is locally exponentially stable. So when you are in the immediate neighborhood of that point, very good things happen. You have exponential convergence rate because Maybe you can even find a norm with respect to which you're locally contracting. Because the Jacobian is given at that point, so you can find the optimal norm for that Jacobian, and then the log norm of the Jacobian is going to be negative in a neighborhood. The only detail is that the norm with respect to which your matrix is, your Jacobian is stable, is Hurwitz, satisfies the LMI for the Hurwitzness, may not be the same norm with respect to which you are non-expansive. So let's keep that in mind, because that's the complication when you have two norms and you try to say that with respect to one norm you're contracting, but you want to compute how the distance is changing the other. That's a little messy. I showed you a picture about that, and I will make that a little exercise. The proof of the exercise is just 2 lines, but all right, fine. So here's the point. The point is that when you start really close, you have exponential convergence. And when you start really far, you have something that I would call linear convergence. So your distance decreases linearly in time. And then as you finally get into the ball near the point, I can prove that the decrease is exponential. Does that make sense? And so we would like to call this, maybe let's give it a name. We call this linear followed by, actually we don't say followed by, linear exponential decay. It's not exponential decay. And you cannot say linear decay, because then if you keep decaying linearly, I mean, you go negative, right? So that's not possible. Allow me to show you a cute little example. Where did you go? Where did you go? Okay, here it is. Suppose that, let's look at this function. This is called the Huber function. It's just a scalar function. This cannot be too hard. This cannot be too hard. All right, this is x. When x is less than 1 in the norm, so therefore between -1 and +1, the function is equal to a half of x squared. It's just a parabola, right? And what does it mean when let me just draw it right. When x is equal to 1, this is equal to 1/2, right? Okay. So then, okay, so if this is 1, that's 1. I should have just drawn this for you. So you have a parabola like that, right? So like this. So here in this neighborhood, the function is strongly convex because the second derivative is going to be equal to +1. Perfect. Outside the interval -1, 1, then, so actually I didn't draw it all that well, but what happens here that now you move, and here this is actually smooth, it's actually differential, it's the correct angle, the correct tangent. It's designed in such a way that, so this curve is that this is a line with angular coefficient -1, and this is a line with angular coefficient +1. And so in fact, if you take the derivative of the Huber function, you get inside here. Let's work inside there. I get the derivative with respect to x of 1/2 x squared. So it's equal to 2/2x. And when you evaluate it at x equal to 1, you get +1. And when you evaluate at x equal to -1, you get -1. And so then I expand the function outside the interval -1, 1 with just a linear function. So the Huber function, they call it a loss function. So imagine you want to penalize an error. You can use the L2 norm of the error, which is a parabola. You can use the L1 norm of the error, which is the L1 norm, right? It's the absolute value looks like this. Or you can say, I would like to have a smooth version of an error, which is quadratic locally, and then it grows linearly. So, all right. So this is, you know, people in optimization have looked at this quadratic linear, it's convex function. It is not, it is strongly convex, only, it's not strongly convex. It's strongly convex only inside here, right? Outside, the derivative is constant. So then it is convex, but you cannot lower bound the Huber loss away from the little interval with the parabola because it's linear. No parabola is going to lower bound it, right? All right, perfect. Okay. Well, you would be surprised if I wouldn't take the gradient, right? I mean, come on, let's take the gradient and see what comes out of it. What do you get out of this? What is the gradient of the Huber function? Well, it's very, very simple. You do the grade. It's simple, other than I just eliminated the formula from the. So you need to remember there was a 1/2 x squared. And then, more importantly, you need to remember. Okay, to write the correct. This is the absolute value because when x is But anyway, it's the absolute value, right? It's this absolute value is the one that would come here. So right. So the absolute value of x minus 1. So the derivative of this is equal to plus or minus 1. And the derivative of that is equal to x. And so then the gradient of the Hilbert function of x is just equal to the saturation function of x, which means that this function is like that. Just a saturation function. I don't even have any parameter here. So this is minus 1, minus 1, minus 1, plus 1, plus 1. Okay. Do you see that, right? Because I am decreasing linearly, so that's minus 1. Then I'm quadratic, so then the derivative is from minus 1. It's linearly changing to plus 1, and then I keep growing, but at rate plus 1. So this is the gradient. This is the gradient. And now I forgot to tell you on day 1. I should have said that when your vector space is the set of reals, then the only norm that you can consider is just the absolute value. There's not much else that you can do. That's the only norm, right? And the log norm associated to the absolute value is just the value of the function itself. So basically, right. What was I going to say? Well, I need to take the log norm of the derivative of the function, right? A log norm of the derivative of the function, which will be the Hessian of the Hilbert function, right? So when I write the one-sided Lipschitz constant of the Hilbert function, well, I need to take, I need to take the derivative, and so that's going to be the derivative. It's going to be plus 1 when x, for x between minus 1 less than equal than x. Well, okay, let's write it the way I wrote it before. X and then 0, right? So that's the one-sided Lipschitz constant. And no, it's correct. It's just that I forgot to put the minus sign. We're going to do minus the gradient of the function, right? Minus the gradient of the, we're going to do the gradient descent, right? So this is minus that is going to be equal. Well, this formula is still correct, but I am interested in computing minus the gradient of the Hilbert function. So that I get a minus 1 here. Okay, so is your dynamical system strongly contracting? Yes or no? Well, it's minus 1 in the interval between minus 1 and 1. So it's locally strongly contracting. And then outside of there, the contractivity rate is 0. Does that make sense? Yeah, does that make sense? So this is a very simple little example, the gradient of the Hilbert function, that tells you that gradient descent for Hilbert function, that there do exist dynamical systems that are weakly contracting everywhere and strongly contracting somewhere. And that's exactly the saturation, x star equal to minus saturation of x, which is a traditional linear system saturation that in control we have studied to death, right? And I don't know, maybe some of you know that whether people have written down formulas for the rate at which this thing converges. And if you think about this dynamical system, which is x dot equal to minus saturation of x, and you ask yourself the question, how quickly do you converge? You will see that the distance decreases linearly until you reach the interval minus 1, 1, and then at that point it starts to decrease exponentially. So that's the linear exponential. It's an illustration of linear exponential. Now, more generally, I can give you a theorem that talks about the gradient descent for a convex function. So this is example number 16, if you haven't had enough of examples from me. F now is not strongly convex. It is just a gradient descent for a convex function. What do we know about it? So some of it are results that have to do with the dichotomy theorem. Other results on this slide are just independent of the dichotomy. It's just the fact that you're doing convex optimization. Does that make sense? So, all right. First of all, the way I've written it here is that there is a dichotomy. It's either case one, either the convex function has no equilibrium. The gradient has no equilibrium. That means the function f has no minimum. That means every trajectory is unbounded. In fact, the classic case of a convex function is a line, and the line does not have any minimum. And if you took the gradient, you just always fall either to the right or to the left. All right. Or the other possibility could be that you have an equilibrium. Okay, so now I have an equilibrium and I have a convex function. Okay, so I have an equilibrium and my convex function, and then what other properties do we know? Well, we know that f is constant on the convex sets of equilibria. So the set of equilibria is convex, as I was hinting at earlier, and the function is constant. Each local minimum is a global minimum. You know that every trajectory is bounded. And actually, you can prove that every trajectory converges to a minimum. And you can prove that each equilibrium is stable, but not asymptotically stable. If the equilibrium is asymptotically stable, then it's also globally stable. And clearly, if you compute the Hessian and the Hessian is strictly negative, then you have these things that I've been describing for you, that is linear exponential decay. And the distance to the equilibrium is a global Lyapunov function. So this is, this, as I said, this theorem here about gradient dynamics, gradient descent for convex functions contains, so based on the theorem for weakly contracting system, but also it uses a little bit more information. Not every one of these points is one that works in general. Just wanted to be clear. All right. Very cute, very cute. So I am out of time. Sorry? Say that again, sorry. Oh, the Euler discretization, yes. The Euler discretization theorem was working well for a strongly contracting system. And what I meant to say by well is that it was working with fixed step sizes. Now, if you have a convex function and you wish to obtain a discrete time algorithm, then of course, this has been studied extensively, but you may not use constant step sizes. All right. So I am past the hour, and I don't desire to insist much more on this. There are two other topics in this advanced area here. One had to do with biologically plausible sparse reconstruction, which was yet another set of examples, a beautiful story behind it. The other one was contraction theory on Riemannian manifolds. I also don't know if all of you are familiar with it. It's a bit of a complicated story. Let me just say that on Riemannian manifolds, you have a space, very generic, very abstract object with a property that you can define curve and perform differentiation operations. The classical example is a sphere. The sphere is a Riemannian manifold, but much more abstract objects can be, like the group of rotations is a Riemannian manifold. The set of positive definite matrices is a Riemannian manifold. And you can, on a Riemannian manifold, you have also an ability to measure the speed of a curve, which is to say the norm of the velocity vector for a curve. So if you're moving along a curve, here, if you're moving along the x curve and you take an arbitrary point here, there is something called the tangent vector. You can take the norm of it, which is the speed of the curve at that point. And then if you take 2 points, if you take a curve and you integrate the speed, that is defined to be the length of the curve. And on the sphere, if you take any 2 points, you can go from one point to the other in many different ways. But I think I was mentioning the other day already that if you take the sphere and intersect it with the plane through the center, you get great circles, and those are the shortest paths on the sphere, the geodesics. And now you can certainly define a vector field to be contracting under the same idea as before. You take 2 points, you let the dynamical system evolve, the vector field, and you track their distance, which is the length of the geodesic connecting them. And you want that distance to be decreasing exponentially fast. It's the same story, it's the same idea, but doing the calculations is more complicated. So there is in the slides, there is a theorem that says, when is it true that, this is the simplest formula in the slide for you to follow, when is it true that the time derivative of the distance between 2 points is upper bounded in the differential inequality sense by minus c times the distance between the 2 points. The symbol d sub g means the distance in the Riemannian manifold defined by the Riemannian metric g. So that's why this is kind of helping you remember that. And remember we wrote an equation that was P Jacobian plus Jacobian transpose P less than equal than minus 2C P. That was the LMI, well, the state dependent, because df is a function of the state, right? X and x, and this must hold for all x's, right? Everywhere in space. So this was the LMI condition that had to hold everywhere in space to ensure that your nonlinear dynamical system was contracting with respect to the 2 norm weighted by P with rate C. And so for the Riemannian manifold case, there is an equivalent condition where instead of P, you write the matrix that represents the Riemannian metric. And so it's really right in the same places as P. And then you write the Jacobian, just like you did before. So this is all identical. It's really identical. The only matter is that you do have an extra term, because you're on a manifold, and this state dependent. Like you can think of G as a state dependent positive definite matrix, and there's an extra term. You need to compute the derivative of this matrix along the flow. So when you have to check contractivity, you have the same terms as before, plus an extra term, which depends upon the state. And the linear matrix inequality, so this is an inequality in the positive definite sense, must hold everywhere in space, just like before. So to some extent, it's also not particularly bad. You can do gradient descent on a Riemannian manifold, and there's a beautiful example. I'll conclude with this example. This is the last one, and then we go. Suppose I give you the so-called Rosenbrock function. Rosenbrock was a famous control person optimization years ago, and he defined this weird-looking function. If you ask me, that's 100 times x1 squared minus x2, all of that squared, plus x1 minus 1 squared. And then you may say, why are you doing this, Professor Rosenbrock? Anyway, you can do the contour plot of that function. So it's like it's a different color scheme here. So I had used red and blue because it was positive and negative. Here, it's always non-negative because it's a sum of squares, right? Yeah, it's a sum of squares. So it turns out that the darker it is, the lower is the value of the function. And so I should have a 3D picture of this. It should not be too hard. But basically, there's like a canyon. It's low, 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 like that. And there's a mountain here, and a mountain there. So this function is not convex. It is not convex because you can take 2 low points here, and then it's not true that the function goes down. In fact, it goes up. So do you understand the visualize the picture? Now, not only it's low here and high everywhere else, it turns out that it is very low here, and you can relatively easily show that the global minimum is at 1, 1. It's really not that hard to show that, even without. So here's the minimum. The minimum is there. The global minimum is there. It's hidden in the middle of the canyon. If you knew that you had to go to the canyon, maybe you can track the minimum of the canyon, you will find a global minimum. Intuitively, what happens is that when x1 is 1, this term is 0. And if x1 is 1, 1 squared is 1. And if I set x2 to 1, then this is also 0. And you cannot go lower than 0 because it's the sum of squares. That's the proof that 1, 1 is a global minimum. And then if you think about it some more, it is the only one. All right, perfect. So now this is not convex. And so if you were to write the, not even, certainly not strongly convex. So if I write the gradient of that, I don't know if it's going to work. Maybe it will not work, or it will take a long time. It will do weird things before converging, maybe. However, if you define something that people call the natural gradient, so the natural gradient is really a tiny modification of the gradient. It's the same thing as before, the gradient of the function. There is a minus sign, but then you use the Riemannian metric, the inverse of it, in order to rotate, to to improve your descent direction. Okay, and it turns out that the function, the Rosenbrock function, is geodesically convex. It means that with respect to geodesics, it is convex, rather than just segments. You know, in a convex function, you draw the segment and you know that the function has to go below. Now you do the geodesic. In the geodesic sense, the function is convex. So in the previous slide, there was a definition of geodesically convex function, which I skipped. Because the Rosenbrock function is geodesically convex with respect to that particular Riemannian metric that I wrote, this G of X matrix, as you see, is not constant. It depends upon X1. Well, then I am delighted to inform you that the natural gradient is globally strongly contracting in a geodesic sense, and it has a unique global minimum to which all solutions converge exponentially fast and blah, blah, blah. And it just so happens to be the case that the way I've written things, unless I made a mistake, the contraction rate is 2. Is the number, the C is equal to 2 for this particular example, the way it's written. Does that make sense? So the punchline of this is that there are notions of geodesic functions on manifolds. And because I promised you this story about positive definite matrices, and I did say I wanted to have an example. So there, I lied to you. This is the last slide, I promise. The manifold, you can take the set of symmetric positive definite functions, and there is something called the Karcher average between symmetric positive definite matrices, and that function is geodesically convex, so it has a unique global minimum. And if you were to write a gradient descent algorithm on the manifold, it would converge. The details of it are not interesting right now. It will take a while for me to review. And with this, I would like to, this is a wonderful paper by Subritsra in the annual conference on learning theory just a couple of years back, entitled First Order Methods for Geodesically Convex Optimization. And so there's a whole area of optimization on Riemannian manifolds and matrix manifolds, and with a little bit of luck, you can use contractivity there as well. Any questions at this time? Yeah.
Why contractivity? Because it gives you a stability property. Are there any converses where you can use the lack of contractivity because it's not stable?
No, I don't know, because even a system that is contracting in one norm can easily be locally expansive in another. And so, yeah, I need to think about it. I have not seen a theorem saying that if your one-sided ellipsis constant is strictly positive everywhere, is it true that you go to infinity? Maybe it's true. I have not thought about it. Yeah, sorry, the good question. Yeah. All right. So as you know, I will be around until next Friday afternoon. If any question comes around, feel free. If you come up with any question, feel free to reach out to me. And with that, I will stop recording.